In the previous session, we were discussing about S matrix. I think we have introduced what S matrix is all about and some unique characteristics of S matrix. And as I have mentioned in my previous session, the S matrix forms the heart of any RF and microwave measurement. In today's session, we will start off with the properties of S matrix, and later we shall go on to derive the derivation for unitary property of a S matrix, which is called as lossless property. So let's start off with the properties of S matrix. The first property of a S matrix is the S matrix is usually a square matrix. The S matrix is a square matrix of order n cross n, where n represents the number of ports in the network. Suppose we are having a two-port network, then n would usually be, it will be a 2 cross 2 matrix. If it's a circulator of say 3 port, then we'll have a 3 cross 3 matrix. So the S matrix is a square matrix. The second property is what we call it as unitary property. The unitary property states that S star transpose into S is equal to identity matrix. If a network with a given S parameter satisfies this condition, then the network is called as lossless network. So if a network satisfies this condition, then the network is called as lossless network. That is, S star transpose into S is equal to identity matrix. The third property of the S matrix is what we call it as symmetry property. If S is equal to S transpose, and if there is a network which has a S parameter, and if that network satisfies this condition, then the network is called as reciprocal network. Another important property of the S matrix is all the diagonal elements of the S matrix will be 0 under perfectly matched conditions. You know that I think if you can recall, S11 represented the input reflection coefficient. So suppose if I have a two-port network, if it's a two-port network and under perfectly matched conditions, S11 and S22 will be 0, which means that the input reflection coefficient and the output reflection coefficient will be 0, making that the system is under perfectly matched conditions. So the next thing that we will do is we will go on to derive the condition for lossless network. And maybe in the next session we will derive the condition for reciprocal networks. Now let us prove that condition for lossless network. We saw that the condition for lossless network is nothing but S star transpose into S is equal to identity matrix. So this is the condition for what we call it as a lossless network. If a network satisfies this condition, irrespective of the number of ports, if a network satisfies this condition, then the network is called as a lossless network. Let's say I have we are going to prove this condition. I have a two-port network at the 4 terminals. Now, and this is say input A1, A2 incident waves, and these are my reflected waves P1 and P2. Now, what is the physical meaning of a lossless network? The physical meaning of a lossless network means power leaving should be equal to power entering. Power leaving should be equal to power entering, which only means that the total power entering is equal to B1 squared plus B2 squared should be equal to A1 squared plus A2 squared. So that means there is no power that is eaten by the network. So the network is a lossless network. So what is the condition? Power leaving will be nothing but B1 squared plus B2 squared. We know that B1 and B2 represent the RMS voltage. So power will be B1 squared plus B2 squared is equal to A1 squared plus A2 squared. So if this condition is satisfied, then we call the network as a lossless network. Let's go on to prove this condition. Let me call this as say 1. Now if you write the S matrix of this two-port network, I can write it like this: B1, B2 is equal to S11, S12, S21, S22, A1, A2, which can also be represented as B, S, A. Now what is this B? B is nothing but B1, B2. Now what we are interested, we need B1 squared plus B2 squared. It's a very small thing. Let's concentrate here. B is equal to B1, B2. If I want B1 squared and B2 squared, what I'm going to do is I'm going to take this B1 star, B2 star into B1, B2. This will give me B1 squared plus B2 squared. Alright, say for example, why this, so what have I done? This is nothing but I have taken the transpose of this fellow. So this will give me B1 squared plus B2 squared. Say for example, let me say B1 is nothing but 0.7 angle 30 and B1 star is 0.7 angle minus 30. Then what will happen? I'll have B1 star into B1. If I multiply, I'll have B1 squared, which will be nothing but 0.49. This plus 30 and minus 30 will cancel. So I'll have 0.49. So you will have that you will be able to get B1 squared. So if I need B1 squared plus B2 squared, what I have to do? I am going to take B star transpose into B. This will be nothing but modulus of B1 squared plus B2 squared. So we can replace, say, let's call this as 2. From 2, substitute 2 in 1, I can get B1 squared plus B2 squared can be replaced with B star transpose into B is equal to A1 squared plus A2 squared can be replaced with, similarly in a similar fashion, A star transpose into A. A star transpose into A. Let's call this as number 3. Now what is B? B is nothing but S into A. B is nothing but S into A. So if you take the transpose, what happens? B transpose is nothing but A transpose into S transpose. You know that when you take transpose, the order gets changed. The order is changed. So I take a transpose, so it becomes A transpose into S transpose. So B star transpose will be nothing but A star transpose into S star transpose. Let's call this as 4. Now substitute 4 in 3. What will you get? Substitute 4 in 3. What will you get? B star transpose is nothing but A star transpose. What is this guy? A star transpose. And what is B? You know B is nothing but S into A. Say S into A. So this will be S A. And what do you have on the right hand side? A star transpose A. Alright. So if you simplify this, I will get, bring the right hand side to the left hand side, I'll have A star transpose S A minus A star, is it A star? Yeah, A star transpose into A is equal to 0. You bring this A star transpose outside. I love A star transpose. A star transpose. Yes. Let's, A is also common in both those fellows, so we'll bring it outside. So it's a matrix, so we should bring it to the right hand side. A is equal to 0. Alright, so now you look at this equation. Can A be 0? If this equation has to 0, either this term should be 0 or A should be equal to 0. Can A be 0? A cannot be 0 because A is the power entering. So what happens? S star transpose S is equal to identity matrix, because this is the fellow which has to be 0. So S star transpose is equal to into S will be equal to I. So this is the condition for a lossless network. Alright, so in the next class what we will be doing is, we will start off with, or we will derive the condition for a reciprocal network. We will derive the condition for a reciprocal network.